Welcome to Naradar Academy. In this video, we are going to discuss about Taylor's and Laurent series expansion. Before going to the proper definition, let me give some concept about Taylor's and Laurent series so that you can understand the concept clearly. Okay, then afterwards I will go to the formal definition. Then in this video, I am going to explain you about 11 solved examples. Okay, so by going through this video, you can you, you can clearly understand how to expand a given function using Taylor's or Lorentz expansion. Okay, now let's come to the concept about this Taylor's and Lorentz series. See, a function, complex valued function f of z will be given to you. You have to expand this in terms of series. Infinite series you are going to expand. So what are the things will be given in your question? One function will be given and then one region will be given. That region will be almost every time you will be given with a circle with center at z0 and radius r. Okay, that is you have to expand this function f of z inside this region about the point z equal to z0. What is this z0? This z0 is the center of this circle. Okay, so simply you have to expand this function f of z about this point z equal to z0. Okay, right. So what is the procedure? What you have to do if you have a problem like this? What you have to do? First thing, you don't bother about whether they have given you to expand in Taylor's or Lorentz series. Okay, there will be no change in the procedure for finding both the series. Everything follow the same procedure only. First thing is you have to find out the singular points. Singular points are nothing but the points where the given function is not analytic. That can easily be found out by equating the denominator of this function to 0. Okay, so what is the first step? We are finding the singular points. That is done by equating the denominator to 0. So if you equate the denominator to 0, you will have the points where the given function is not analytic. Okay, then with that singular point and this region, this is a circle, no, circle with center at z0 and radius r. Inside this circle only we are going to expand this function. So you check whether any of these singular points are lying inside this circle or not. Only I am telling only inside, not on the circle. That is why I have put the sign strictly less than. So any of the singular points are lying inside this circle or not. Okay, two cases arise. There is no singular point inside the circle. If there is no singular point inside the circle, then what happens? Your function will have an expansion with all positive powers of z minus z0. Positive powers means what? Z minus z0, z minus z0 the whole square, z minus z0 the whole cube plus etc. Like that only you will be having when there is no singular point inside the circle. That means all the singular points are lying outside this circle. In that case you will have only positive powers of z minus z0. And what is the region of convergence? This will also you may be asked. Okay, what is the region of convergence? Here the region of convergence will be what is given there in the question, that is called the region of convergence. Okay, the problem is simple in this case when there is no singular point inside the given region. Understood? Now let's come to the other case. Suppose if I have a singular point inside my circle, what happens? So let me explain here with this diagram. See, this is the point, the center point is there, no, this is z0 and this is radius r. The outer circle is there, no, it is of radius r. You please keep this in your mind. This is a circle, that is I am representing only the points inside the circle. So whenever you draw the circle you have to draw it in dotted line. It is not clearly available in the video, that is why I draw it as a full circle. But whenever you are drawing, you draw it as a dotted circle. That means the points on the boundary are not included. Okay, so what is the first thing I am doing? I am with the z0 as center, I am drawing a circle of radius r. So this is the region given in the question. Okay, in the first step I find out some singular points. In that one, out of the singular points, one of the singular point A is lying inside my circle. This point here I put one dot, no, that is a point A and that is a singular point which is lying inside my circle. So there is a singular point A lying inside my circle. So what will happen to the series expansion? The series In this case, the series will contain negative powers of z minus a. That is, a is a singular point, no? It will contain negative powers of z minus a. What do you mean by negative powers? That means 1 by z minus a, 1 by z minus a the whole square, and so on, etc. Okay, right? This will contains negative powers of what? Z minus a. And not only that, positive powers of z minus z naught will also be there, because z naught is a regular point, no? So positive powers will be there. Okay. And what about the region of convergence for this case? Okay, what is the region of in the previous case, when there is no singular point inside the circle, I clearly stated the region of convergence is what is given there in the question. That itself will become the region of convergence. But here the region of convergence will be find out in this way. See, this is the point A, no? With z naught as center, you draw a circle so that this A lies on the boundary. Okay, understand? That radius may be taken as R1. Okay, what I am doing here, this is the original circle. Outer circle is the original circle given in the question. Now inner circle, how I am drawing? With z naught as center, and I am drawing a circle which passes through A. Boundary is on the boundary, this A point lying. Okay, let this radius be equal to R1. Then my expansion, whatever I got here with positive and negative powers, no, this expansion is valid only in the annular region. Annular regions mean what? Outside the small circle and inside the bigger circle. Okay, why I am telling like that? Because here my series is containing both positive and negative powers, no? The positive powers of z minus z naught is valid inside or inside all the points in the bigger circle. Okay, but this negative powers are there, no? That negative powers are valid only outside the small circle. It is not valid inside the small circle. So combine, when you take both the things combined together, the region of validity will become the annular region. This is what Taylor's and Laurent series expansion. That means when there is no singular point inside the given region, you will have only positive powers of z minus z naught. When there is a singular point inside the given region, okay, you will be having negative powers. Okay, this is the concept. Now let me give you the proper definition for Taylor's and Laurent series expansion. See Taylor series. Let f of z be analytic in a region D containing z naught. Then f of z can be represented as a power series in z minus z naught given by f of z equal to f of z naught plus z minus z naught f dash of z naught plus etc. so on. No need to memorize all these things. I am not going to use this definition for doing problems. Okay, I will explain you simply how to do the problem. Okay, just for understanding of the concept, I am going through this definition. So what is Taylor series means? When your function is completely analytic within the whatever here is saying open disk containing center at z naught contained in D. So when your given function is completely analytic, there is no singular point means what? It is completely analytic. Then your function can be expanded in positive powers of z minus z naught. You see z minus z naught is coming only in the numerator. This is called Taylor series. So Taylor series expansion comes only when you don't have any singular points inside the given region. Okay, only positive powers. So next, what about Laurent series? Okay, for Laurent series, what we are having is that, see, we have both positive and negative powers. So why do we have this positive and negative powers means here we are defining in between what? Annular region. Okay, right. This is enough for now. Let me directly go to the problem. For doing problems, you don't need to look into this definitions. Okay. Now, before starting the problem, let me give you two expansions, binomial expansions, which play a vital role in doing these types of problem. One is 1 minus x the whole power minus 1. Another one is 1 plus x the whole power minus 1. The expansion goes like this. 1 minus x the whole power minus 1 is 1 plus x square plus x cube. All are positive terms. Okay. What is the region of validity? This expansion, these two expansion, both these expansions are valid only when your modulus x is less than 1. Okay, if your modulus x is equal to 1 or greater than 1, both these definitions are invalid. Okay, if you take x is equal to 1 by 2, 1 by 3, 1 by 4, okay, in that way this expansion is true. But if you take x is equal to 2, 3, 4 or like that, both these expansions are invalid. Okay, you can check with any, you give any value for x and you check. So whenever you are using these two definitions, you have to write mod x is less than 1. Okay, this is very important for doing problems in Taylor's and Lorentz series. Okay, now let's start with the first problem. Expand f of z equal to z minus 1 by z plus 1 about z equal to 0. Here I didn't mention whether it has to be expanded in Taylor's or Lorentz series. Even in the question, if they have given about Taylor series or Lorentz series, you don't bother about it. Both are same only. Whatever way you do, if it contains singular point inside the circle, you will have negative powers. Otherwise, you will have positive powers. So you no need to bother about whether it is Taylor's or Lorentz. Okay. So expand f of z equal to z minus 1 by z plus 1 about z equal to 0. What is the first step I told you? Find out the singular points. So what is the singular point? How do you obtain the singular point? Just equate the denominator to 0. What is the denominator here? Z plus 1. Z plus 1 equal to 0 implies Z equal to minus 1. So this is the singular point. What is the singular point? Z equal to minus 1 is the only singular point. Okay, right. Now, what is the point given here? Z equal to 0. Z equal to 0 means with 0 as center, you have to draw a circle. Okay, with 0 as center, you have to draw a circle. And another one is with z equal to 0 means you have to take it like mod z less than 1. That means mod z minus 0, 0 as center and 1 as radius. You take 1 as radius, then only we can make use of this binomial expansion. Okay, my expansion, my series expansion will contain z minus 0, z minus 0 the whole square, z minus 0 the whole cube, etc. Okay, so I am taking, what is the radius I am taking here? 1 unit. So here you see 0 as center and 1 as radius, I draw a circle. Now you see this is the singular point, no, z equal to minus 1. Where is it lying? It is lying on the boundary. This is minus 1. Okay, not plus 1, this is minus 1. Okay, this minus 1 is lying on the boundary. You don't bother whether it is lying on the boundary or outside. That doesn't matter. Only if it lies inside, okay, that will become a singular point inside. So now, as of now, there is no singular point inside the region. Okay, so your question will contains only positive powers. This is for verification only. Okay, so this is the procedure I explained you earlier, right? Now let me come to the problem. So f of z equal to z minus 1 by z plus 1. So the singular point is minus 1. So no need to bother about it. You have to expand about z equal to 0. Now this is the denominator. No, if you bring the denominator to numerator, it will become 1 plus z the whole power minus 1. Just to expand this using the formula that I have given already. So what is the expansion? 1 minus z plus z square minus z cube plus etc. That's all. Now here you multiply. So multiply the entire term with z and then multiply with minus 1. Then some of the terms get cancelled. So finally you are getting minus 1 plus 2z minus 2z square plus etc. What is the region of validity here? Modulus z less than 1. Okay, understand? Right. Then next problem. Expand f of z equal to z minus 1 by z plus 1. The same problem I have taken. Previously, the same problem about z equal to 0 we have expanded. Now we are going to expand about z equal to 1. Okay, about z equal to 1 means your series will contain terms z minus 1. That is z minus 1, z minus 1 the whole square and so on etc. Now again, let us come here. See, z equal to minus 1 is the singular point, no? Okay, now I have drawn the diagram in the next page. See, about z equal to 1 only you have to expand, no? So let me simplify the denominator and let me go to the next page. Z minus 1 is there in the numerator. No need to bother about it. In the denominator, you should bring the term like Z minus 1. Then only you will get powers of Z minus 1. Okay, so Z minus 1 plus 1. That is I am adding and subtracting 1 here. Then only I will get Z minus 1. So Z minus 1 plus 1. Already 1 plus 1 is there, no? Okay. So Z minus 1 by So this I can write it as 2 plus z minus 1. Why I am keeping z minus 1 here? Because I want to expand about z equal to 1. So my term should be like what? Z minus 1, z minus 1 the whole square and so on etc. Now already I told you I am going to make use of only these two expansion, 1 plus x or 1 minus x. So here I am having it like 2 plus z minus 1. So 2 plus z minus 1 means you take 2 outside. Okay, if you take 2 outside, what will you get? 1 plus z minus 1 by 2. Okay, now we have to bring it to the numerator. So what will you get? F of z equal to z minus 1 by 2 into 1 plus z minus 1 by 2 the whole power minus 1. Okay, now you expand. This is like 1 plus x the whole power minus 1, no? So what will you get? 1 minus x plus x square minus x cube plus etc. And what is the region of validity? Whenever you have term like this term should be, modulus of this term should be less than 1, no? So modulus of z minus 1 by 2 is less than 1. Okay, right. Let me multiply this z minus 1 inside. Don't multiply individually. In the previous problem, I multiplied individually because there I expanded about z equal to 0. But here I am expanding about z equal to 1. That means z minus 1 should be there. So you multiply z minus 1 as a single term. So 1 by 2 into z minus 1 minus 1 by 2 into z minus 1 the whole square plus 1 by 2 square into z minus 1 the whole cube etc. And what is the region of validity? Mod z minus 1 is less than 2. Okay, now we have completed the problem. Let me check with the diagram. Now only I am getting the region of validity. Now let me check it with the diagram. So about z equal to 1 you are expanding means you have to take 1 as the center and you have to choose the radius. No, here what is the, from by solving the problem itself we have obtained the radius is equal to what? 2 units. That means from 1 you have to take 2 units on all the 4 direction. You complete the diagram. So for this problem also, what is the singular point you are getting? Minus 1. That minus 1 is lying here only. It is not lying inside. So your expansion will contain only positive powers of z minus 1. Okay, right, good. Then next one. Next problem, expand f of z equal to 1 by z square about z equal to minus 1. So as usual, let us check the singular point. Equate the denominator to 0. Okay, z square equal to 0. So z equal to 0 is the only singular point. Okay, right. So you keep it here itself. Let us come to the problem. We will solve as before and then I will finally I will tell you where the singular point is lying. Now we have to expand about z equal to minus 1, no? So here I am having only z. So add and subtract 1 because I should get it like z plus 1. I have to expand it with z plus 1, z plus 1 the whole square, z plus 1 the whole cube. So I am adding and subtracting 1 here. Within the square only I am adding and subtracting. So z plus 1 minus 1 the whole square. Okay, right. Now you take what? Minus 1 outside. So when you take minus 1 outside, it comes along with the square. So minus 1 the whole square into, so this minus 1 will become plus 1 minus z plus 1 the whole square. So this will become plus 1. When you bring to the numerator, it will become 1 minus z plus 1 the whole power minus 2. Now this is like 1 minus x the whole power minus 2. What is the expansion for this? 1 plus 2x plus 3x square plus 4x cube plus etc. Where modulus x is less than 1. In the same way, I am expanding it here. 1 plus 2 into z plus 1 plus 3 into z plus 1 the whole square plus etc. Where here in the place of x, what do I have? Z plus 1. So mod z plus 1 must be less than 1. Only in this region, this expansion is valid. So what is this region? This region is a circle with minus 1, center at minus 1 and radius 1 unit. So center at, this is the previous diagram. Here itself I will explain with minus 1 as center and 1 unit as radius means your circle will come here. A small circle will be coming here. So 0 will be lying on the boundary. Okay, that is if you have the axis like this. Okay, right. So what is the center here? Minus 1. So minus 1 means here it is minus 1. 1 unit radius only. So on the left, right and top and bottom you move 1 unit. So here it will be minus 2. Here it will be 0. Here it will be plus 1. Here also it is minus 1. So this will be the circle. So, okay. So this will be the circle and this 0 is lying on the boundary only. 0 is the only singular point. No, that 0 is lying on the boundary. So inside this circle there is no singular point. So this expansion is valid. Okay, right. Then the next one, expand f of z equal to 1 by z square in the region mod z minus 2 less than 2. If the region is given, it will be well and good. Okay, we can easily identify where the singular point lie. The same problem, same f of z in the as in the previous question, but the region is different. Okay, right. So here also 0 is the singular point, and here what is this circle with the 2 as center, and the radius is also equal to 2. So 2 on the real line you take 2, and then radius 2 units means on each side you take 2. So again here 0 is lying on the boundary. So within my circle, inside my circle, there is no singular point. Okay, right. Now mod z minus 2 is less than 2 is given, no. But for writing the binomial expansion, I must have less than 1 only. So both sides you divide by 2. So mod z minus 2 by 2 is less than 1. Okay, so your expansion should be like z minus 2 by 2. All your expansion should contain positive powers of z minus 2 by 2. So for that, what you should do? 1 by z square is there, no? Within the square you add and subtract 2. So z minus 2 plus 2 the whole square. Okay, now my expansion should contain z minus 2 only, no? So this z minus 2 don't disturb. Here this 2 is there, no? You take this 2 outside. Since this is within the square, when you take it outside, it will become 2 square. 2 square of 1 plus z minus 2 by 2 the whole square. Now you bring this term to the numerator and then you expand. So this is like 1 plus x the whole power minus 2. Again the expansion is 1 minus 2x plus 3x square minus 4x cube plus etc. Where this is your x term, no? Whenever you are writing the binomial expansion, your x term will be what? Less than 1. So mod z minus 2 by 2 is less than 1. Okay, so this is the expansion where the region of validity is mod z minus 2 is less than 2. Understand? Okay. Then the next problem. Expand f of z equal to z square minus 1 by z plus 2 into z plus 3 in the region mod z less than 2. Okay. Right. As usual, equate the denominator to 0. We get z plus 2 equal to 0 and z plus 3 equal to 0. So z equal to minus 2 and z equal to minus 3. Two singular points are there, minus 2 and minus 3. Now let us check this circle. This is the circle with center at origin and radius 2 units. So center, origin and radius 2 units. So this is the circle. So this minus 2 and minus 3. Minus 2 is lying on the boundary and minus 2 is here. Minus 2 is lying on the boundary and minus 3 is lying outside. So there is no singular points inside the circle. Okay. So when you expand, it will contain only positive powers of z. Positive powers of z. Powers of z only there. Right. Okay, before doing the problem, look at this one. Product of terms there in the denominator, no? So we cannot do it as it is. When you have product in the denominator, you have to split it by partial fraction. But for applying partial fraction, denominator's power should be more than the numerator. But here numerator is also degree 2, denominator is also degree 2. When you multiply these two, no, degree 2 only you are getting, no. So when numerator and denominator are in the same degree, first you divide and then we will split it by using partial fractions. Okay, right. First I am dividing the numerator by the denominator. In the numerator it is z square minus 1, no. So z square minus 1 divided by z square plus 5z plus 6. So one time. So it will be what? Z square plus 5z plus 6. Change the sign. Z square get cancelled. So what I am getting? Minus 5z. Here it is minus 6 minus 1 will be minus 7. So how will you write? This is the quotient and this is the remainder. As an example I have given here. If you divide 13 by 5, 2 5s are 10. Remainder is 3. So how will you write this 13? 13 is equal to quotient 2 plus remainder by this divisor 5. In that way, here 1 plus quotient is 1 plus minus remainder is minus 5z minus 7 by the divisor is what? Z square plus 5z plus. In this way you have to write. Okay, right. Now I have to split this term. Now the numerator degree is less than the denominator. Now I have to split this by using partial fraction, because for expanding in Taylor's or Laurent series, the denominator should contain single term. That then only you can easily expand. Okay, then only you can find out the region of validity also clearly given. Right. So I am going to split this by using partial fraction. These are linear factors, no, that is power 1 only. So I can write them as a by z plus 3 plus b by z plus 2. Now you cross multiply. So minus 5z minus 7 by z plus 3 into z plus 2 equal to a into z plus 2 plus b into z plus 3 by z plus 2 into z plus 3. Now both left and right side are having same denominator, they will get cancelled. So minus 5z minus 7 equal to a into z plus 2 plus b into z plus 3. Collect the terms containing z and constant term. So z into a plus b plus constant term 2a plus 3b. Here coefficient of z is minus 5 and constant is minus 7. So a plus b is minus 5 and 2a plus b 3b is minus 7. Now you see, let us solve these two equations. Now 2a plus 3b equal to minus 7. No? Multiply this equation by 2. So 2a plus 2b equal to minus 10. So subtract. These two terms get cancelled. 3b minus 2b is b equal to 3. So b equal to 3 means if you substitute it here, a equal to minus 8. So let us substitute in the value of f of z. What is f of z? 1 plus this value, no. So 1 plus minus 8 by z plus 3 plus 3 by z plus 2. Now it is easy for me to do the calculation. Now about which point I have to expand for this problem? In the region mod z less than 2. That means whatever I have, it should be like less than 1 only, no. So divide both sides by 2. So z by 2 is less than 1. So z by 2 I can bring in this term, because if I take 2 outside, automatically I will get z by 2 here. But what about this side? Here I am having z plus 3. So when you take 3 outside, it will be 1 plus z by 3 only. But before expanding, you have to check whether this is less than 1 or not. You see, modulus z is less than 2. This is given in the question. But 2 is always less than 3, no? So this is less than 3. Now you take only these two terms. Mod z is less than 2, less than 3. That implies mod z is less than 3. That implies mod z by 3 is less than 1. So mod z by 2 is also less than 1. Mod z by 3 is also less than 1. Why I am doing like this is because one of my term is containing z by 3. Another term is containing z by 2. So both the terms I am going to have here. Right? Okay. Now let us expand. So it's equal to 1 minus 8 by 3 into 1 plus z by 3 the whole power minus 1 plus 3 by 2 into 1 plus z by 2 the whole power minus 1. So let us expand. Okay. Then when you write the region of validity, this is valid in mod z less than 3. This is valid in mod z less than 2. So when you write them both of them together, the common intersection is what? Mod z is less than 2. Okay. Good. Then the next one. Expand 1 by z square minus 4z plus 3 in the annulus 1 less than mod z less than 3. Okay, right. Now let us take the denominator, equate it to 0. First I have factorized it, z minus 3 into z minus 1. When you equate it to 0, 3 and 1. 3 and 1 are the singular points. What about this circle? This is the annular region, no? This is the circle with the 0 center. With the 0 as center, you draw a circle of radius 1 unit and draw a circle of radius 3 units. Okay, z equal to 1 is here. Okay, 1 is here and 3 is here. Don't bother about 3. 3 is lying outside only because we are not taking points on the boundary. Okay, you have to look at the outer circle only. What I said earlier in the beginning of this video, see, take the outer circle, z equal to 3. Okay, inside this circle I have a singular point. What is that singular point? 1. 1 is my singular point. So z minus 1 term should come in the negative power. This z minus 1 is there, no? That should come in the negative power. That means 1 by z minus 1, 1 by z minus 1 the whole square, like that. And z minus 3 should come as positive powers. That means z minus 3, z minus 3 the whole square, etc. Can you understand? This is what I told you in the beginning of the video. And the region of validity will be in the annular region, that is in between these two circles, outside the smaller circle and inside the bigger circle. Okay, before proceeding to the problem, first you have to split the denominator by using the method of partial fractions. So since the factors are linear, you can take them as a by z minus 3 plus b by z minus 1. Now you cross multiply and cancel the denominator. Finally I am getting 1 equal to a into z minus 1 plus b into z minus 3. Okay, right. So now you collect the terms containing z and constant. So z into a plus b plus minus a minus 3b. So equate a plus b to 0 because no z terms are here, no. So a plus b equal to 0 and minus a minus 3b equal to 1. Okay, right. So here from this I am getting a equal to minus b. Put it here. So b minus 3b minus 2b equal to 1 or b equal to minus half. When you substitute it here, a equal to plus half. So let us substitute all these values in my f of z. So f of z equal to 1 by 2 into 1 by z minus 3 minus 1 by 2 into 1 by z minus 1. Okay, what I told you earlier, see this 3 bigger circle is there, no? Bigger circle is having one singular point. What is that singular point? 1. So z minus 1 will come in the negative powers, and what is that? Z plus z minus 3 should come in the positive powers. But here they have given about z equal to 0 only we are expanding, because here mod z is less than 3, no, about z equal to 0 only we are going to expand. So how to do the expansion? After splitting into partial fraction, take the given region. 1 less than mod z less than 3, no, right? Now you take it into two parts. 1 less than mod z and mod z is less than 3. See, 1 less than mod z means what? Mod z is greater than 1. So when you have like this, bring this z to this side. So it will become 1 by mod z is less than 1. Okay, right. Then here, when you come to this side, you have 3 on the right hand side, no? You should have only 1, right? So divide both sides by 3. Mod z by 3 is less than 1. So what I have? 1 by mod z, and what is this? Z by mod z by 3. So your expansion should contain powers of 1 by z and powers of z by 3. So for this one you should have what? Z by 3. That means take 3 outside. For this one you should have 1 by z. That means what? Take z outside. So 1 by 2 into, take minus 3 outside, minus 3 into 1 minus z by 3. This is where you are determining the positive and negative power. So this part is important. Okay. So here, whether you can take 3 outside or z outside, but whichever you have to take, that is being decided here. So here in this factor you have to take 3 outside, so it will be 1 minus z by 3. But in this factor you have to take which one outside? Z outside, because 1 by z is less than 1, right? Okay, so what will you have? Minus 1 by 6 into 1 minus z by 3 the whole power minus 1, minus 1 by 2 z into 1 minus 1 by z. Okay, right. Now let us expand using the binomial expansion. So it will be minus 1 by 6 into, right, 1 plus z by 3 plus z by 3 the whole square plus z by 3 the whole cube plus etc. Minus 1 by 2 z into 1 plus 1 by z plus 1 by z the whole square plus 1 by z the whole cube etc. Right. If you want, you can simplify further. Otherwise, you can leave up to this. Understood? Next one. Expand f of z equal to minus 1 by z minus 1 into z minus 2 in the region mod z less than 1. Okay. So first let us find the singular points. 1 and 2 are the singular points, but this is the circle with center at 0 and radius 1 unit. So both the singular points are lying outside the circle. So we will have only positive powers. Now let us see. This has to be split up by using method of partial fraction. As discussed in the previous problems, you have to take it like a by z minus 1 plus b by z minus 2. Cross multiply, cancel the denominator. I am getting minus 1 equal to a into z minus 2 plus b into z minus 1. Collect the z terms and constant terms separately. Equate left and right side. Z term is there, no z term is there, no. So a plus b is 0 and minus 2a minus b equal to minus 1. So a equal to minus b. So if you substitute it here, a equal to 1 and b equal to minus 1. So this is my f of z. So how to expand? Take the given region. What is given? Mod z is less than 1. So here I can just take minus sign outside. So it will be 1 minus z. So if you bring it to the numerator, it will be like 1 plus z plus z square plus etc. So the first term has no problem. For the second term, either you should take 2 outside or z outside. So for that, look at this term. Mod z is less than 1. No, divide both sides by 2. So z by 2 is less than 1 by 2. But 1 by 2 is what? Less than 1. So how can I write? Mod z by 2 is less than 1. Therefore, here also you should get only positive power. So take minus 2 outside, 1 minus z by 2. And you write the expansion 1 plus z by 2 the whole square plus etc. So both the terms are having positive powers. Why they have, both of them have positive powers? Because both the singular points are lying outside. Okay, right. So only positive powers will come in the expansion. Then the next one, the same problem I have taken, but the region is different. 1 less than mod z less than 2. So about the point 0 only you are expanding, but when the region is given in the annular region, that means one term should be 1 by z, the other term should be what? Z by 2. Okay, from here itself we can find out. One term will be, you take this region. This is the previous question only. That is why I have taken f of z directly here. Now let me come to the region. 1 less than mod z less than 2. So take the first part alone. Mod z is greater than 1 and second part is mod z is less than 2. This implies 1 by mod z is less than 1 and this implies mod z by 2 is less than 1. So for this factor you have to take z outside, then only you will get 1 minus 1 by z. For this factor you have to take 2 outside, then you will get z by 2. Okay, so 1 by z into 1 minus 1 by z the whole power minus 1 plus 1 by 2 into 1 minus z by 2 the whole power minus 1. Now you expand. So 1 by z into 1 plus 1 by z plus 1 by z square plus 1 by z cube plus etc. Here 1 by 2 into 1 plus z by 2 plus z by 2 the whole square plus etc. Since this is also 1 by z, you multiply it inside. That's all. Okay, right. Then next, the same problem again I have taken with a one another different region. Mod z greater than 2, the same question. So using partial fraction I split the denominator. Okay, mod z is greater than 2 implies what? 2 by mod z is less than 1. Okay, 2 by mod z. For this term it is okay. 2 by mod z means if you take z outside, you see here, if you take z outside it will become 1 minus 2 by z. This term is okay, but what about this term? For that term, see, this is what you are having, no? Divide both sides by 2. Both sides by 2, what will you get? This 2 get cancelled, so 1 by mod z is less than 1 by 2. But 1 by 2 is always less than 1 only, no? So what I have, 1 by z is also less than 1. So for this term you should get it as 1 by z. So for that you have to take z outside. Take z outside, it will be 1 minus 1 by z. Bring it to the numerator. So 1 by z into 1 minus 1 by z the whole power minus 1 minus 1 by z into 1 minus 2 by z the whole power minus 1. Now you expand. 1 by z into 1 plus 1 by z plus 1 by z square plus 1 by z cube plus etc. Here minus 1 by z into 1 plus 2 by z plus 2 by z the whole square plus 2 by z the whole cube plus etc. What is the region of validity they have given? Mod z is greater than 2. Now since all are 1 by z's only, no, so I have multiplied both 1 by z's inside, and then after that, since both are having similar terms, I have subtracted. Okay, so you can simplify up to uh, um, uh, uh, as well as possible you simplify, otherwise you can leave here itself. Okay, because they are not going to follow any standard pattern, so you can leave here itself. Right, next one, expand f of z equal to z plus 4 by z plus 3 into z minus 1 the whole square in the region 0 less than mod z minus 1 less than 4. Okay, now first we have to split this by using partial fraction. Okay, because here we have a product of terms, no? So here one is linear factor, another one is quadratic factor. In that case, how will you take in partial fraction? A by z plus 3. Linear factor you take a by. This quadratic factor, no? This factor you have to take one term without square and another term with square, that is b by z minus 1 plus c by z minus 1 the whole square. This is the procedure when you take by using partial fractions. Okay, now you take LCM and cancel the denominator. Now z plus 4 equal to a into z minus 1 the whole square plus b into z minus 1 z plus 3 plus c into z plus 3. For finding the values of a, b, c, put z equal to 1, so that these two terms will get cancelled. I will get only c. So 5 equal to 3 plus 1 4c. So c equal to 5 by 4. Next, put z equal to minus 3. So these two terms get cancelled. We will get the value for a. So minus 3 plus 4 1 equal to 16a. Because here minus 3 minus 1 minus 4. Minus 4 square is 16a. So a equal to 1 by 16. Next, for finding the value of b, put 0 for z. 0 if you put, what will you get? 4 equal to a minus 3b plus 3c. Already you know the values of a and c. Substitute the values for a and c and you can find out the value of b. So after finding the ABCs, substitute in f of z. So this is my f of z. Keep it now here. Let me come to the region. What is the region given here? Mod z minus 1 is greater than, sorry, less than 4. Now the singular points are given here. What are the singular points? Equating the denominator to 0, we get z equal to minus 3 and z equal to 1. These two are the singular points. Let's see whether they are lying inside or outside the circle. See, this is a circle with center at 1. So with 1 as center, you have to draw a circle with radius 4 units. So from here, you move on 4 steps, left, right and top and bottom. So you get a circle. Okay, so inside this circle, this 1 is lying, no, 1 is lying inside, and minus 3 it is lying on the boundary only, so you can leave. So only one singular point is lying inside. So this z minus 1 will come in the negative powers. Okay, see, z minus 1 is less than 4, so z minus 1 by 4, z minus 1 by 4 is what? Less than 1. So how will you do this one? Already you are having 2z minus 1 terms, so they are already in the denominator, so you keep them as it is. No need to disturb these two terms. Okay, understood. Next, here this is z plus 3. No, I should write it in the form of z minus 1. So for that, what I am doing is add and subtract minus 1. Okay, in the place of z plus 3, z minus 1 plus 1 plus 3. Minus these two terms I am not going to disturb because already they are in the form z minus 1. So no, don't disturb the remaining two terms. Here only z minus 1 plus 1 plus 3 is 4. So 4 plus z minus 1. So you take 4 outside. So it will be like what? 1 plus z minus 1 by 4. You bring it to the numerator and expand. Okay. So how you are getting 1 by 64 into 1 minus z minus 1 by 4 plus z minus 1 by 4 the whole square minus z minus 1 by 4 the whole cube plus etc. Right. Minus these two terms. Okay. So this expansion contains two negative powers of z minus 1 and the remaining are positive powers of z minus 1. Okay, right. Next one, expand f of z equal to z plus 4 by the same question, but the region is different. Mod z minus 1 is greater than 4. In the previous problem, mod z minus 1 is less than 4. Here it is greater than 4. So how will you get? Bring this z minus 1 to this side. So we get what? 4 by z minus 1 is less than 1. Okay, so as usual in the previous case, keep this z minus 1 as it is. Don't disturb z minus 1. Only this term you have to change. So add and subtract 1, z minus 1 plus 4. So in the previous case, you take 4 outside. Because it is less than 4, so you take 4 outside. But here it is greater than 4, no? So how will you take? You have to take z minus 1 outside. So it will be 1 plus 4 by z minus 1. Bring it to the numerator and then you expand. So 1 minus 4 by z minus 1 plus 4 by z minus 1 the whole square etc. And these two terms are kept as it is. Okay. If you want, you can simplify further. So since all are containing z minus 1 in the negative powers, I am multiplying this term inside. So I am getting 1 by 16 into z minus 1 into, see, this is 1 by 16 into z minus 1 into 1. Here minus 1 by 16 into z minus 1. So these two terms get cancelled. So I am having this with this term multiplied with the remaining term. So what I am getting finally? Minus 1 by 4 z minus 1 the whole square plus 1 by z minus 1 the whole cube minus 4 by z minus 1 the whole power 4 plus etc. Now look at these two terms, similar terms only, no? So if you subtract 5 minus 1 will be 4. 4 by 4 z minus 1 the whole square. So it will be simply 1 by z minus 1 the whole square. The remaining terms there is no change. So just you write them as it is. Okay, right. That's all. Hope you understand all the problems that I have discussed here. If you have any doubts, you uh, share it in the comment section. I will try to answer your problems. Okay. Thank you.